Infrared radiation technology, commonly referred to IR technology, is a pivotal element in a wide range of modern applications, from everyday consumer electronics to advanced scientific research. Infrared radiation is a type of electromagnetic radiation with wavelength longer than those of visible light, extending from the nominal red edge of the visible spectrum at 700 nanometers to 1 millimeters. This range includes near-infrared, mid-infrared, and far-infrared regions, each with distinct characteristics and application. In essence, IR technology leverages the unique properties of infrared radiation for various purposes, including tomography, night vision, and environmental monitoring. By detecting and analyzing infrared radiation emitted or reflected by objects, IR technology provides invaluable insights that are often invisible to the naked eye. This presentation will delve into the significance in advancing numerous fields, instruments, and diverse applications, potential benefits, and challenges, and future development and innovation. The significance of infrared radiation technology. First, it enhances the imaging and sensing capabilities. Infrared radiation technology is crucial for thermal imaging, enabling the visualization of temperature distribution in various environments. This has profound implications for areas such as medical diagnostic and industrial inspection. Second, advanced scientific research. Infrared spectroscopy is a cornerstone in scientific research, allowing for the analysis of molecular composition and interaction. This is particularly significant in astronomy and environmental science. And last but not least, it enhances the security and surveillance. Infrared cameras and sensors are vital for security and surveillance, providing the ability to monitor areas in complete darkness. This is essential for military and defense that use night vision equipment and thermal scope to enhance situational awareness and operational capabilities.
We're going to move on to scientific instrumentation and application concepts. Based on scientific instrumentation, night vision technology relies on sophisticated scientific instruments known as infrared detectors. These detectors are important components that capture and convert infrared radiation into visible images. There are two main types of infrared detectors used in night vision devices, which are cold and uncooled detectors. Cold detectors require cryogenic cooling to extremely low temperature to minimize thermal noise and maximize sensitivity, while the uncooled detectors operate at ambient temperature and has more compact, lightweight, and energy-efficient device. The example for cold detectors is military-grade goggles, while the uncooled detectors is security camera. In terms of application concepts, infrared radiation technology works based on the principle of thermal radiation and heat signatures. Thermal radiation is the emission of electromagnetic waves by a body due to its temperature. It is a crucial concept in infrared technology as it allows one to detect and measure the temperature of objects without physical contact. Night vision devices use infrared radiation to detect heat signatures and create visible images, enabling users to see in low light or no light conditions. The concept of heat signatures refers to the unique thermal patterns emitted by objects. Even in complete darkness, objects emit thermal radiation based on their temperature relative to their surroundings. Night vision devices can detect and visualize these heat signatures, allowing users to identify objects based on their thermal contrast with the environment. These are the components of a night vision devices, also known as NVD. First, we have infrared illuminators, which emit infrared light to illuminate the surroundings, enhancing visibility in low light conditions. Second, the lenses. It collects and focuses incoming light onto the detectors. The third one is the detectors. It detects incoming infrared radiation and converts it into an electrical signal. And lastly, the signal processing and display. It processes the electrical signal to generate a visible image displayed to the user.
Next, I'm going to explain to you guys about detailed exploration about our chosen technologies, which is the night vision. But before that, I'm going to tell you guys about the most important things you guys have to understand, which is the amount of energy in light wave is related to its wavelength. Which is, it means the shorter wavelengths have a higher energy, or a longer wavelength have a less energy. I'm going to explain to you guys how thermal imaging works. First, a special lens focuses the infrared light emitted by all the objects in view. Then the focus light is scanned by a phased array of infrared detector elements and create a very little temperature pattern called thermograph. It only takes about 1/30 of a second for the detector array to obtain the temperature information to make the thermograph. This information is obtained from several thousand points in the field of view of the detector array. Then, the thermograph created by the detector elements is translated into electric pulse. Then, these impulses are sent to a signal processing unit, a circuit board with a dedicated chip that translates the information from the element into data for the display. The signal processing unit sends the information to the display, where it appears as a various color depending on the intensity of the infrared emission. The combination of all impulses from all images creates the image. Next, I'm going to explain to you guys how image enhancement works. Firstly, a conventional lens or called objective lens capture ambient light and some near-infrared lights. The gathered light is sent to the image intensifier tube. In the most NVDs, the power supply for the image intensifier tube receives power from two N cell or two AA batteries. The two outputs a voltage about 5 volts to the image tube components. The image intensifier tube has a photocathode which is used to convert the photon of light energy into electrons. As the electrons pass through the tube, similar electrons are released from an atom in the tube, multiplying the original number of electrons by a factor thousands through the use of microchannel plates or MCP in the tube. An MCP is a tiny glass disc that has a million microscopic holes or microchannel in it, made using a fiber optic technology. The MCP is contained in a vacuum and has a metal electrode on either side of the disc. Each channel is about 45 times longer than it is wide, and it works as an electron multiplier. When the electrons from the photocathode hit the first electrode of the MCP, they are accelerated into the glass microchannels by the 5,000 volts burst being sent between the electron pairs. As electrons pass through the microchannels, they cause a thousand of other electrons to be released in each channel using a process called cascade secondary emission. Basically, the original electrons collide with the other channel, exciting the atom and causing the electrons to be released. These new electrons also collide with other atoms, creating a chain reaction that results in thousands of electrons leaving a channel where only a few enter. An interesting fact that the microchannel in the MCP are created at a slight angle about a 5 degree to 8 degrees bias to encourage electron collision and reduce both ion and direct light feedback to the phosphors on the output side. At the end of an image intensifier tube, the electron hit the screen coated with the phosphors. This electron maintain their position in relation to the channel they pass through, which is provide a perfect image since the electrons stay in the same alignments as the original photons. The energy of the electron causes the phosphor to reach an excited state and release photons. These phosphors create a green image on the screen that has become to the characterized night vision. The green phosphor image is viewed through another lens called the ocular lens, which allows you to magnify and focus the image. The NVD may be connected to the electron display such as a monitor, or the image may be viewed directly through the ocular lens.
Night vision technology, which often utilized in infrared radiation, is implemented in various real-world applications. First, we have military. The night vision technology is extensively used in military operations for surveillance, reconnaissance, and target acquisitions during low light or nighttime conditions. Military-grade night vision goggles, scopes, and camera amplify available light or detect thermal radiation to provide enhanced visibility in darkness. Second, we have security. Security for the night vision cameras and surveillance systems are deployed in security applications to monitor areas such as borders, critical infrastructure, and high security facilities during nighttime hours. This system provides continuous surveillance and early detection of intruders or suspicious activities. And lastly, we have wildlife observation. Biologists, conservationists, and wildlife researchers utilize night vision technology to observe nocturnal animals without disturbing their natural behavior. It aids in studying animal behavior, population dynamics, and ecological interactions during nighttime hours. These real-world implementations demonstrate the diverse applications and benefits of night vision technology across various sectors, contributing to enhanced safety, security, and efficiency in low light or nighttime conditions.
Next, we will be moving on to the potential benefits and challenges in infrared radiation night vision technology.
Potential benefits of IR radiation in night visions. IR night vision technology offers several potential benefits, but it also comes with its own set of challenges. For the benefits, firstly, it's enhanced visibility in low light conditions, which is when the night comes. IR night vision technology enables users to see clearly in low light or total darkness by detecting and amplifying infrared radiation emitted by objects, providing enhanced situational awareness. Second, infrared radiation technology night visions also improves surveillance and security. IR night vision is widely used in security and surveillance applications, allowing for the monitoring of areas during nighttime or in low light conditions, enhanced perimeter security and threat detection capabilities. Thirdly, the search and rescue operations. IR night visions aid search and rescue teams in locating individuals in low light conditions such as darkness, smoke, or dense foliage, increasing the chances of successful rescues. And lastly, automotive safety. Infrared night vision system in vehicle enhance driver visibility by detecting pedestrians, cyclists, and large animals on the road, helping to prevent accidents, especially in low light conditions.
This is the overview of automotive night vision system by near-infrared technology. Car night vision frameworks helps in cautioning the drivers with respect to the nearness of potential perils before they become obvious through the use of either a warm camera or infrared light sources. Various techniques utilizing infrared sensors have been recommended in the writing so as to distinguish vehicles in far-infrared (FIR) pictures. Pictures from cameras with infrared are relied upon to improve the impression of the driver under low light conditions.
Application of night vision also have their own challenges, which is firstly we have the cost because high quality IR night vision technology can be expensive, limiting its widespread adoption in certain applications, particularly in consumer electronics and civilian sectors. Second, they have limited range. The effective range of IR night vision devices may be limited, especially in adverse weather conditions of environments with high humidity, reducing their effectiveness over long distances. Thirdly, the power consumption. Some IR night vision systems require significant power consumptions, which can be a challenge in battery-operated devices or remote locations where power sources are limited. And lastly, detection of camouflage objects. Certain camouflage techniques, such as using materials that absorb or reflect IR radiation, can make objects harder to detect using IR night vision technology, potentially compromising its effectiveness in certain scenarios.
Here are some of the future developments in night vision. First one is enhanced image processing, which AI can reduce noise, sharpen details, and improve contrast in infrared images. This makes it easier to interpret and act on the data provided by night vision devices. The second one is longer battery life. Improvements in sensor technology and power management will extend battery life, allowing night vision devices to operate longer without needing recharges. This is crucial for military missions, wilderness expeditions, and disaster response operations. The third one is augmented reality, also known as AR integration. Combining night vision with AR can overlay critical information on the user's views, such as navigation path, object identification, and tactical data. This enhances situational awareness and decision making. And last but not least, digitally fused images. Future night vision devices will merge images from thermal images and visible light image intensifiers. This digital fusion provides a comprehensive view, combining thermal data with enhanced visible light for better clarity and detail.
Night vision technologies has been around for decades, and technologies continues to evolve and improve. Through the use of digital night vision, unparalleled clarity can be achieved, revolutionizing the way we perceive the world around us. Other traditional night vision technologies that relies on image interference to digital night vision technology utilizes a digital signal processor, also known as PHY380, to generate a near-infrared image from an image sensor. This image is then displayed on a screen, providing a much clearer picture than that of analog night vision devices. Digital night vision technology is much more efficient than analog night vision devices, as they are able to provide higher resolution images with greater clarity and an increased field of view. This technology has been used in the military for decades and is now becoming more widespread in the civilian market. Digital night vision technology can be used in a variety of applications such as surveillance, hunting, and recreation. Furthermore, the use of digital night vision technology has opened up a wide range of possibilities that were impossible with analog night vision devices. Next, wide focus technology has enhanced the contrast and perception. By using the wide focus technology, a heightened level of contrast and perception can be achieved, offering a new level of clarity and detail. This technology has been successfully used in latest night vision devices, providing an improved level of clarity for military and law enforcement applications. Wide focus technology works by capturing from a near-infrared illuminator and converting it into visible light, allowing the observer to see details not available in regular night vision devices. This technology offers improvement of contrast and visibility in low light conditions, the ability to see more colors in detail in the dark, and it enhances clarity and detail in image and video in the dark. Wide focus technology provides a higher level of clarity and detail, giving users the ability to see more in low light conditions. This technology is becoming increasingly important in military and law enforcement applications, as it allows for more precise and accurate observation in the dark. Last but not least is the vision system combining night vision and thermal imaging. The combination of night vision and thermal imaging capabilities into a single device, vision system provides users with an enhanced level of detail and clarity, allowing them to better observe their environment regardless of lighting conditions. These systems are composed of two distinct imaging technology, and a processor will merge this image into a single composite. Night vision technologies relies on image interference that amplify light, while thermal imaging utilizes infrared radiation to capture image. The processor combines the two streams of data to create one image. The result composite image allows user to observe features not visible in either of the two individual images. This includes the detection of objects in perfect darkness and the ability to differentiate between objects based on their thermal signature. Such systems have application in a variety of scenarios, from surveillance to search and rescue operations. Vision systems are also becoming increasingly popular among hunters and hobbyists, as they allow users to observe the environment in the darkness in conditions.
In conclusion, night vision technology rooted in the exploration of infrared radiation has revolutionized our ability to see in the dark. From military operation to wildlife conservation, its applications are diverse and far-reaching. As we look at the future, the ongoing innovation in this field promise even a greater advancement in night vision capabilities.